So as we saw, the analysis of algorithms typically involves computing the time complexity T of n as a function of n, which is the input. Okay, and now we want to compare, say, two functions. So supposing you want to compare f of n, which is say n cubed, and we want to know whether this is better or worse than say g of n, which is 5000 n squared, let's say. So supposing we have two algorithms, one takes n cubed, the other one we have computed somehow takes 5000 n squared, and we want to know which is better. So one way is to kind of extrapolate the values to all numbers in between. So we know that n equal to 1.5 doesn't make any sense, but we can just treat these as functions over the reals, and then we can draw graphs. So maybe we have the following graph, okay, for n squared. And then we observe that initially, so let's start it here. So the initial value of the n cube graph is below the n squared graph. So it looks like f of n, because it doesn't have this big constant, is actually better. But as n grows, sooner or later, it's going to happen that f of n actually crosses g of n. And in fact, in this case, it's easy to see where this happens. So this will happen when n cubed is equal to 5000 n squared, which is precisely at the point 5000. Right? So when n crosses 5000, before that, f of n is the winner in the sense that it's smaller. And beyond that, it's going to be bigger. And not only that, this gap is going to grow. Right? So as we go bigger and bigger values of n, the gap between f of n and g of n will grow. So although g of n initially had a disadvantage because of this constant, f of n actually is much worse. Right? So what we're really saying is that we're really interested in some notion of orders of magnitude. Right? So we're saying n cubed, n squared, these are what we're really worried about, not the 5000 or the 6 or whatever the coefficients are. Right? So we're going to ignore coefficients. So sometimes this is called ignoring constants. Ignore constant factors. Okay? So we're going to say that, okay, 5n squared and 3n squared are pretty much the same, but 5n squared is much better than 2n cubed. Okay? So overall, this has a name, and this is called asymptotic complexity. So this is the behavior in the limit. Okay? So behavior as n tends to infinity. This is what we're really interested in. Now this has a bearing on something else that we talked about, which is this notion of basic operations. Okay. So remember that we gave this example saying that we could have swap xy as a basic operation, or we could say only assignments are basic, in which case we would have to break this up into 3 steps. First we store the value of x, then we overwrite x with y, and then we restore y from temp. Right? Now the point is that if we take one of these is equal to 3 of these. So if we count swaps and we count assignments, we get a factor of 3. But if we ignore constants, okay, this doesn't matter. Right? So the notion that we are tying ourselves to a notion of asymptotic complexity, where we look at orders of magnitude, where we don't worry about constants, is intimately related to the fact that we can be flexible about our choice of basic operations, so that so long as we assume something reasonable about them. So we will group together functions of a similar type. So we'll have typical functions. Okay, so we might be interested in looking at problems where t of n is something like log of n. Okay, so it might be 5 log of n, it may be 1000 log of n, but so long as it's a constant, doesn't matter as long as the operative part is log of n. Or we might be looking at t of n is n. So this is something which is linear in the input. Or we might be looking, as we saw last time, at things which are n squared, or something in between, like n log n, and so on. Okay, so we will look at all of these and see how it matters in terms of the efficiency. Now remember that we said last time that we can do approximately 10 to the 10 operations per second. Okay, so this is our running assumption about typical CPU speeds. Okay. So now one can draw a chart. Okay, so one can take all these functions. So for example, we can take functions like log n, say n log n, n squared, n cubed, 2 to the n, and even n factorial, right? And now we can say what happens when, say, n is 10. Okay, so when n is 10, log n is about 3. n of course is about 10, n log n is n times log n, which is 30, n squared is of course 100, n cubed is 1000, 2 to the n is already also 1000, and n factorial is something like 10 to the power 6. So now if you go to 100, then this 3 becomes something like 7. This 10 becomes of course 100 because n is 100. Now 100 times log n is about 700, so let's keep it at 700. Okay, n squared is going to be now 10 to the power 4, n cubed is going to be 10 to the power 6. Now 2 to the n is already going to be something astronomical, 10 to the power 30. And n factorial in fact turns out to be something so humongous, it's at 10 to the power 157. Right? So now if you see this as our 10 to the power 10 as our boundary, you can see that already in going from 10 to 100 here, we have crossed the boundary of feasibility. Right? There is no way we're going to be able to solve any problem of size 100 if the algorithm is exponential or factorial, because it's just going to take way too long to do any computation. Right? So we can go one step further. So supposing we go to 1000, okay, now log grows very slowly, it goes to about 10. This is 1000. N log n is about 10 to the power 4 now. Okay, n squared is 10 to the power 6, and now n cubed is approaching the limit of what we can do, 10 to the power 9. If we go one step further, 10 to the power 4, then here we have something like 13. Here we have, of course, 10 to the power 4. Now n log n is going to be about 10 to the power 5, but n squared is now approaching the limit, and n cubed has gone over. So now n cubed has now crossed the limit of what we can do. Okay. So in other words, if you have a cubic algorithm, we can do some inputs with our assumption about 10 to the 10. We can do assumptions, inputs where the sizes are a few thousands but not 10,000. Right? So we continue in this vein. So if you go to 10 to the power 6, for example, okay, then here I will have 10 to the power 12, and so I cannot go to 10 to the power 6 with an n squared algorithm. Right? But now it will take me all the way down to 10 to the power 10 before I reach 10 to the power 11 over here. Right? So this way we can see that depending on the efficiency as far, even in terms of orders of magnitude, we can see how drastically what we can solve reduces as our efficiency goes down. Right? So notice that if I have 10 to the power 10 over here, okay, at this point, okay, then log of n is actually still something like 33. Okay, so that's really incredible that if we have something input of the size 10 to the 10, and a log n algorithm will take only 33 steps. Okay, and already with the input of size 10 to the power 6, an n squared algorithm is taking 10 to the 12 steps. So this chart sort of tells us dramatically why it is important to separate orders of magnitude when one compares functions. Another point to note is that exponential functions essentially are useless. Unless you have inputs which are really small, like 10, 20 or something like that, there's no hope that an exponential algorithm will end in any time which is reasonable. And also n squared, we've already seen this with the sorting thing, n squared, so usually all polynomials, that is all functions that look like this, are considered to be efficient in some abstract sense. But in a concrete sense, this is already a huge divide, going from n log n to n squared. So n squared algorithms typically can be really inefficient, even for real size inputs that we see in day-to-day life. Now the other thing we saw last time is that t to the n, t of n means different things, because there is no such thing as a uniform input of size n, right? So it depends on the input. So to illustrate this, let's look at a simple algorithm, one which asks us how we can search for an element in an array. So we want to search for k in an array A. Okay, so this is the problem that we want to do. So here is an algorithm. We start with the index 0. Okay, so we have n elements. So we start at the index 0, and so long as we are within the array and we have not found k, we increment the index. So what this says is this while loop will exit as soon as we find, so this exits when we find an index such that ai is equal to k, or if we reach I is equal to n, right? And when we exit, we check whether we crossed n or not. If we reached n, that means we didn't find it. Otherwise, we found it. So if we did find it, we return the index where we found it. If we didn't find it, we return -1. Okay. So now let's see two extreme scenarios. Okay. So the first extreme scenario is that k is actually equal to a0. Okay. So now the loop exits in one step. Okay. And the other point is k is not in a at all. Here the loop takes n steps. Right? So we have to go through the entire array to find out that it's not there. So in a natural sense, this is the best possible thing that we could happen, and this is the worst possible thing that we could happen. Now typically our algorithm has to run on all different types of input that the user supplies, and we have no control over whether something is there or is not there. So when we make an estimate about the running time of the algorithm, typically this worst case estimate is the most realistic thing we can do, because it gives us an overall upper bound for how much time this algorithm takes. So this motivates looking at different notions of complexity. So the first, as we said, is worst case. So worst case complexity, okay, asks us to look at, for each n, take the input of size n that takes the longest time, right? So this is going to be the value that we will put as T of n. So T of n will be the longest time it takes for any input of size n. And we add this up over, we plot this for each n and we get a function, okay? So in a very natural way, this is an upper bound, okay? So if this is how much time it takes in the worst case for each n, then overall for all inputs, it takes at most this much time. So if we do a sequence of computations involving the algorithm, we can add up T of n for each input and we'll get something which takes, the actual algorithm can take no more than that much time, okay? And how do we construct the worst case input? So we can construct worst case input by looking at the algorithm, right? So as we saw in the previous thing, we looked at the algorithm and we saw what it is. It says we start at 0 and it goes to the end and it exits at the end if it has not found it. So from this we know that the worst case input would be one where it will not find it. Yeah? So this is something that we typically can reverse engineer. We can look at an algorithm and force it to take as much time as it should or as it possibly can, and from that we can reconstruct a worst case input. So worst case inputs are one sensible way of measuring the running time of an algorithm. Another possibility, of course, is to be optimistic. So we can do this thing called best case complexity. So like in the previous example, okay, we can look at the best possible input. But of course, this is in some sense not at all sensible. For instance, we could just fix this by having a lookup table, right? So supposing we have an algorithm for square root, okay? So the algorithm is the square root of n. We can have a function which says something like, if n is equal to say a large number, okay, return 10 cubed, else compute. Now, this would suggest that for this algorithm, 10 to the power 6 is the best case input. But of course, it makes no sense because the algorithm is really tuned to doing 10 to the power 6, right? So a best case input in practice is rarely used because it's not really a meaningful estimate of any kind. A more relevant thing would be to say what happens on the average. Okay? Now it could be that worst case is too pessimistic. Okay? So worst case is rare. So if the worst case is rare, then the worst case complexity is very pessimistic. We are making provision for a complexity or a time that never really takes. So there are some examples of this. For instance, there is a well-known algorithm called quicksort. Okay, and if you do a worst case analysis of this, you get something which takes time proportional to n squared, but in the average case, okay, it takes n log n, which is significantly better, as we saw in the table a few slides back. N log n works much better than n squared. We also saw this in some informal examples in the previous lecture. Okay. Now, how do you do this? Well, you actually have to in some sense enumerate all inputs. I mean, not physically, but you have to account for all inputs of size n and compute the average time. Okay, so this sounds easy, but it's actually quite hard. And the reason that is quite hard, there are two reasons. Okay, the first reason is, what are all the inputs? Okay, so for instance, in sorting, you could quickly look at the fact that it doesn't really matter what the numbers are. So you can assume that if you have n inputs that are actually 1 to n, and so then you can have all permutations of 1 to n, right? So we could say that all inputs of size n consist of all different permutations of size 1 to n, of the numbers 1 to n, and you can explicitly compute for each of these how much time, say, quicksort does, divide by the total number of such permutations with n factorial, and get an estimate. But in general, this is hard to do. It's hard to just even come up with a valid set of all possible inputs of size n. So remember, for instance, the problem that we had about the video game with the points on a plane. Now, how do you enumerate all possible distribution of points, endpoints in the plane? It's kind of very hard to even come up with that number, and it's not in general something which is reasonable. Okay. The other thing that is more subtle is that not all inputs are equally likely. Okay, so in some sense, you can do an analysis of this kind if you assume that every possible input of size n occurs with the same probability. But in general, this is not the case. So you need some kind of underlying probability distribution, and this is hard to come by again. Right? So for these reasons, average case analysis is very rare, and sorting is probably one of the few examples where a reasonable average case analysis has been performed for any reason, for any complex algorithm. The last category of complexity is something which comes typically in the context of data structures, and it's called amortized complexity. Okay, so the word amortization actually comes from economics. So it's something where you pay some fixed costs now, and then you recover the cost later. For instance, supposing you wanted to rent or buy. Okay, so you have a difference between rent or buy. Okay? So if you rent, then you pay per use. So buy, you have a fixed cost, and then you have free usage. So imagine it's DVDs. Okay, so supposing it is, say, 100 rupees per DVD rental. Okay, and then the cost of the DVD is some 500. Then if you're going to watch the DVD 5 times, at least it makes sense to buy it. But if you're only going to watch it once or twice, you might as well rent it. Okay, so this is a notion of amortization from economics. And now in our context, it arises typically in data structures. Okay, data structures are objects in which you store data with some properties. For example, you might want to maintain a sorted array of numbers. Right? So now when you add things to it, you have to keep the array sorted. So there is a certain cost you pay, but then if you're also going to be searching for things in it, you can do binary search, and that cost will be recovered. Right? So basically you have some expensive operations, and then to balance it, you have some cheap ones. Okay, and they average out in some sense. So now if you took only the expensive operations as your worst case estimate and you multiplied it by the number of operations, you get a very pessimistic estimate of the overall cost. Whereas if you do this carefully, it will work. Okay? So we will see an example later on where we have to maintain a disjoint union of sets. Okay, so there is a very well-known algorithm which uses a data structure to keep track of a disjoint union of sets. And this algorithm, the data structure that we use for the disjoint union of sets, it will turn out that it has low amortized complexity, although the individual operations can be quite expensive. Okay. So to summarize, what we have seen is that we are typically interested in asymptotic complexity, that is orders of magnitude. Right? Then we've also saw in that chart how the feasibility boundary drops drastically as the order of magnitude of the function increases. And then we saw different types of measures that we could use. So we had worst case, best case. So worst case is a kind of upper bound. Best case is a kind of optimistic bound and probably not useful. Then we could also, in some cases, get a nice average case analysis like quicksort, but this is hard to do. Okay, and then for data structures, so it's not average case, sorry, but average complexity. And we have amortized complexity for data structures, which allows us to measure across a sequence of different operations what the total cost is going to be. So these are different ways that we will look at algorithms. Most often we will typically be doing this one, right? So the worst case is the most common analysis, in some sense because it is the most reasonable one, and also because it is in some sense the easiest to do, because average case is kind of hard to do.